Good morning, honors chemistry students. The next element we're going to look at today and examine as part of our atomic structure and quantum mechanics review is beryllium, which is in row 2, column 2, immediately after lithium. The particular isotope of beryllium we're going to look at is Beryllium-9. In this particular isotope of beryllium, it has an atomic number of 4, thus it has 4 protons, and its mass number is 9. And bear in mind that we identify various isotopes by their mass number. So we're going to refer to this as beryllium-9. Once again, the 4 represents the Z value, which is the atomic number, which is equal to the number of protons, which also equals the number of electrons, which in this case is 4. The 9 represents what we affectionately refer to as the A value, which is also known as the mass number, which is equal to the number of protons plus the number of neutrons, which in this case, we've identified this particular isotope of beryllium as having an atomic number of 4, therefore it has 4 protons. And by the same token, to determine the number of neutrons, if you subtract the atomic number from the mass number, you get a value of 5. So 4 and 5 is equal to 9. We say that beryllium is a member of row 2 of the periodic table, also known technically as period 2, because it has enough elements to start filling the second energy level. We say it's a member of column 2, which is also known as group 2A. Bear in mind that the A represents what we refer to as the representative elements. And the representative elements, the Roman numeral represents the number of valence electrons. So group 2A metals represent elements that have 2 electrons on the highest occupied energy level. We say that beryllium is a member of the alkaline earth metal family. Okay, it's one of the 4 named groups on the periodic table. As always, I want you to represent an atomic energy level diagram according to Bohr's theory. You represent the nucleus with a box that's divided in 2. The top part of the box represents protons. The bottom part of the box is represented by neutrons. In this particular isotope, it has 4 protons and 5 neutrons for a mass number of 9. Then we need to set out to represent the 4 electrons. We know according to quantum mechanics, the first energy level holds a maximum of 2 electrons, which would be the n equals 1 or k shell. Once the first energy level is filled, by the Aufbau principle, you start filling the second energy level. And we're going to place 2 electrons to the right because according to quantum mechanics, each energy level, kind of circle challenged early in the morning, these are big circles. Each energy level has an s sublevel with 1 orbital that holds 2 electrons. So we're going to say that this is the second energy level, which is also known as the L shell. Note that this is a member of group 2 because it possesses 2 valence electrons, which are the electrons on the highest occupied energy level, or another way to think about that is the number of valence electrons in the highest occupied S and P sublevel. So that being said, these 2 electrons are why it's placed in group 2A metals, the alkaline earth metals. Moving along, to represent the valence electrons, I want you to create an electron dot representation. And in the electron dot representation, you draw the symbol for the element along with two valence electrons, which in this case there are two dots. The next representation I want you to think about once again is that of orbital notation. Orbital notation is a way of accounting for the placement of electrons and energy levels by what we refer to as the Aufbau principle. That's a German word, which means to build up. So theoretically, according to quantum mechanics, when you start placing electrons in energy levels, you place them in energy levels that are lowest in energy first near the nucleus, and start placing them in higher energy levels and sublevels. So therefore, the first energy level here, we say, according to quantum mechanics, has just one s sublevel, which holds two electrons of opposite spins. Again, we use arrows to represent electrons of opposite spin. The up arrow represents a clockwise spin, and theoretically the down arrow represents a counterclockwise spin, because when you place two spinning objects that have rotational motion near one another that are similarly charged, they repel in opposite directions. Once the first energy level has its full complement of electrons, we go ahead and start filling the second energy level, which according to quantum mechanics also has an s sublevel called the 2s, which can hold two electrons. By the way, when we immediately pair electrons in the s sublevel, we're still honoring Hund's rule, which says each orbital in a sublevel gets one electron before you pair them up. Since there's only one orbital in each s sublevel, we can then immediately pair them up with the next electron. That being said, to represent the valence electrons and to write their address, we would write what's called the electron configuration, which in this case, we have two electrons in an s sublevel on the first energy level. So we'd simply write 1s2, and we have two electrons in an s sublevel on the second energy level, so we'd write 2s2. So the configuration for beryllium is 1s2, 2s2. And you can see that the two subscripts, 2 and 2, is 4, sum to the number of protons in the nucleus as well as the number of electrons around the nucleus in its neutral atom. That being said, the last representation, which we're going to have to squeeze in here a little bit, is the Cartesian coordinate system, in which you use an xy plane to represent the arrangement of valence electrons. Remember that the vertex of this graph represents the nucleus, around which we're going to draw the first energy level, which holds two electrons, and we're going to represent the next two electrons on the n equals 2 energy level in such a manner. So that is beryllium. The next element we're going to consider is nitrogen. We're going to skip boron and carbon for the time being. Thank you and have a great day.